Hello everybody. Welcome to our video solutions to the relatively small Quiz 7. This is from our fall 2021 Math 106 course. That's differential equations and integral calculus. And this quiz is all about sequences. So we just have a couple of problems. The first one is actually, well, it's split up into three problems where we're given three different sequences and we want to use the properties of sequences, and namely sequence convergence, to determine whether or not these sequences converge, and if they do, what their limit is, right? So let's start with, well, how about A? So the first thing that I'm looking at here, I say, well, I got a polynomial over a polynomial. Okay, so this is called a rational function. And the degree of the numerator polynomial is 4. The degree of the denominator polynomial is 3. So immediately I should be saying this thing should be going off to infinity. This is going to be a divergent sequence because the degree in the numerator is greater than the degree in the denominator. Now let's actually make an argument as to why that's going to be true. So let's copy this function down. All right, I'm just copying. 3n to the fourth plus 8n squared minus 6n plus 2 over 4n cubed minus 3n plus 1. And what I'm going to do is I'm going to take this denominator here and look at the highest degree term, n cubed, and I'm going to factor an n cubed out of everything I see. So I can rewrite this as, so I'm going to factor out an n cubed from the top, and I get 3 times n plus 8 times 1 over n minus 6 times 1 over n squared plus 2 times 1 over n cubed. And in the denominator, we're going to get, let's see, I factor out an n cubed, and I'm left with 4 minus 3 times 1 over n squared plus 1 times 1 over n cubed. Right, and of course, you could redistribute this n cubed if you wanted to make sure I had done this correctly. We know that our n is eventually getting very, very big, certainly greater than 0, so it's okay to cancel these n cubes. All right, so as long as n is not 0, we can cancel, and in the long run, that is definitely going to be the case. All right, so now I can just copy all the rest of this junk. And we divide, and we have 4 minus 3 times 1 over n squared plus 1 times 1 over n cubed. Now, since I'm looking for the limit, then I'm just asking what's happening as n goes to infinity. And as n goes to infinity, well, let's see. Let's start from the bottom. This 1 over n cubed, 1 over n squared, those all go to 0. All right. So this goes to 0. This will go to 0. This 4, actually, that just stays at 4. This 2 times 1 over n cubed, that's going to go to 0. 6 times 1 over n squared, that goes to 0. 8 times 1 over n, that goes to 0. Which, by the way, right, like, why did I know all these were going to 0? Of course, we had this great assumption in the problem, right? We know that if you look at any of these pieces, right, that they're all going to go to 0. But then there's this last piece here, the 3n. Everything else is going to 0. Everything else is going to 0. And of course, we're allowed to look at it piecewise, right? Top and bottom and within each of the sum ends because of the properties of sequences, right? But this 3n does something different. As n goes to infinity, this 3n blows up. So we have this numerator having 4 pieces, 3 of which go to 0, but 1 of which blows up to infinity. And so this whole numerator is going to go off to infinity. And of course, the denominator is going off to 4 plus 0 plus 0, which is 4. So in total, the numerator goes to infinity, the denominator goes to this constant 4, and so the ratio must be going to infinity. All right, therefore, the sequence A must be diverging. Okay, it's diverging to infinity. All right, what about sequence B? Well, sequence B, we're going to basically play the same game, only here we notice that the degree of the numerator and the denominator are the same, which should make us believe that the limit will be the ratio of those leading coefficients, right? So the limit should be 6 over 3. But let's give an argument. So I start with 6n squared minus 3n plus 1 over 3n squared plus 100n minus 13. And just like before, I want to factor out the lowest degree term. So in the sense of I look at the numerator and the denominator and I ask which is the lowest degree polynomial. In this case, they're the same. And the degree is 2. So I'm going to factor out this lowest degree, n squared. So in the numerator, I get n squared times 6 minus 3 times 1 over n plus 1 over n squared. And in the denominator, I factor out an n squared and get 3 plus 100 times 1 over n minus 13 times 1 over n squared. I can cancel the n squareds because, again, I can assume n is not 0. And I get 6 minus 3 times 1 over n plus 1 over n squared over 3 plus 100 times 1 over n minus 13 times 1 over n squared. And now, just as before, as n goes to infinity, well, 6 goes to 6, but 1 over n goes to 0, 1 over n squared goes to 0, this 1 over n squared goes to 0, this 1 over n goes to 0, and 3 goes to 3. And so in total, the numerator is going to go to 6 plus 0 plus 0, which is 6. The denominator is going to go to 3 plus 0 plus 0, which is 3. And so the numerator goes to 6, the denominator goes to 3 by the properties of sequences. The entire sequence will go to 6 over 3, or 2. So our sequence B converges to 2. All right, finally, we have sequence C, and it's defined a little bit differently. It doesn't have a polynomial over a polynomial. It's an arctangent function over a polynomial. Now, the polynomial in the bottom, that's pretty easy. We know that's going to go to infinity as, well, n goes to infinity. But this arctangent function, we're going to have to know a little something about arctan. So why don't we draw a picture of tan? Because, man, whoever remembers anything about arctan? The tangent function between negative pi over 2 and pi over 2 looks something like this. So this tells us that as the input of the tangent function goes to pi over 2, the output goes to infinity. Now the arctan is the inverse function. That means you just reverse the roles of the inputs and the outputs. So as n is going to infinity, that means the input of the arctan is going to infinity. The output gets closer to pi over 2. So this arctan is going to go to pi over 2. So we have a fraction where the numerator is converging to pi over 2. The denominator is blowing up to infinity. And so in total, the ratio is going to go to 0. Okay, there we go. We're using our properties all over the place. And hopefully this gives you a little bit of insight as to what you should be writing down for these problems.